Hey y'all, welcome back. Let's take a look at tonight's homework. The first thing I want to point out is that I've included this formula up here. This is something that you're going to need to know. You're going to need to know how to find a projection vector. And this is the formula for if you're projecting B onto A. So the vector that you're projecting is going to be this bigger one, okay? And then the subscript is what you're projecting onto. So B is casting the shadow on A, if you're thinking of it like that. Now, if you swap these, you would swap all the variables as well, although the dot product will be the same whether you do A dot B or B dot A, so you don't really have to worry about that too much. But if I do end up projecting A onto B, I would change these to B. So let's find the projection of B onto A. So here, we're taking the vector 1, negative 1, and projecting onto 6, negative 8. So to find that vector, which should be a pretty small vector since we're projecting B is pretty small. 1, negative 1 doesn't go very far. So I'm expecting to get kind of a small number for the projection vector as well. So let's go ahead and calculate this out. What I'm going to do is just highlight this and just start plugging away with all the values that were given in this problem. So to find the dot product, I'm going to do 6 times 1 plus negative 8 times negative 1. And then we need to find the magnitude of the vector that we're projecting onto. So A is acting as like our floor that we're projecting onto. So to find the magnitude, and we will end up squaring that, but we'll have the square root, which when you square it kind of goes away. But just for the sake of being accurate here, we've got 6 squared plus 8 squared. And then that whole thing should be squared. So I wonder if I can make this look a little better. Or is that just, yeah, that's just how it's going to be. So we've got 6 squared, which is 36, 8 squared, which is 64, and I'll simplify all those separately. Now, all of this is clearly going to just simplify to be a single number, and we're going to take that number and we're going to multiply it by the vector that we're projecting onto, that floor vector, which is 6, negative 8. So as soon as I simplify this whole behemoth, I'm going to distribute that to both the 6 and the 8. So just to kind of walk you through the simplification process here, and you can put all this in the calculator, to be quite honest. It's probably easier to do that. But I just want to walk you through how what you get in the calculator is attained. So 6 times 1 is just going to be 6. Negative 8 times negative 1 is going to be positive 8. 6 squared is 36. Oops. And 8 squared is going to be 64. Okay. Taking the square root and then squaring it, that's just going to cancel itself out. So we can just delete those. And then 36 plus 64, well, let's do 6 plus 8 would be, what would that be, 14. And then 36 plus 64, 90 would be 100. So this is a fraction that we can distribute to both the 6 and the negative 8. It appears that we can simplify this. Both of these are divisible by 2, so we can reduce this to 7/50ths. So when we go to distribute this and we multiply 7/50ths by 6 and 7/50ths by negative 8, just to be on the safe side, I'm going to do this in the calculator. I believe we'll be able to reduce too, like 7 times 6 is going to be 42, so that's reducible. So just to kind of save some time here, I'm going to pull up the old calculator, and we'll evaluate that way. So we've got 7 alpha y equals, not just y equals. 7/50ths times 6. Okay, so that's 21 over 25. And then, so a little bit less than 1. You know, we said it was going to be kind of a small vector here. And then we've got 7/50ths times negative 8. Which gives us negative 28 over 25. And so that would be the projection vector right there. So you're going to be solving pretty much all of these on this front page the same way. But let me show you how it would work with two three-dimensional vectors. We're going to use the exact same formula here. Just got to be a little bit more careful on how you evaluate each of these little parts, each of the pieces here. So a times b is going to be, in this case, 1 times 0, okay? We're in good shape so far, plus 0 times 2, okay, that's going to be 0 as well, plus 3 times 1. And then the magnitude here of vector A would be the square root of 1 squared plus 0 squared plus 3 squared. And that whole thing will be squared times vector A, which is 1, 0, 3. So we'll simplify all this. 1 times 0 is 0. 0 times 2 is 0. 3 times 1 is 3. So we get 0 plus 3, which is obviously just 3. In the denominator here, we've got 1 squared is 1. 0 squared is 0. So that's just going to go away. 3 squared is 9. So we get the square root of 10 squared. So recall from the last problem that when we square a square root, we're just left with whatever the radicand is. So you're just going to be, like the square and the square root effectively cancel each other out. So we just get 10 down there. Now we're going to distribute the 3/10 to each one of these. So we should get 3/10 times 1 is 3/10. 3/10 times 0 is 0. And then 3/10 times 3 is going to be 9/10. So our vector, our projection vector, is going to be 3/10, comma 0, comma 9/10. And that's number 2. Number 3, looks like we've got some two-dimensional vectors, and they're written in linear combination form rather than component form, but that's not going to really affect anything as far as how we're going to compute these. So for the dot product, we've got 3 times, if you don't see the coefficient on one of these, it's just going to be 1. And if this one isn't missing it, but let's say we were missing like the j component, then you would just assume that that's 0. So 3 times 1 plus 5 times 4 is going to give me the dot product. And then we're going to have the square root of 3 squared plus 5 squared times the vector 3, 5. And just to stay consistent, I'm going to stick with component form here, even though the vectors were originally written as a linear combination. It doesn't really matter which form you go in, so whatever you prefer is fine. I like using component form. So now we'll simplify all that stuff inside the parentheses. 3 times 1 is 3. 5 times 4 is 20, so this should be 23. Over 3 squared is 9. 5 squared is 25. So let's see, 25 and 9 would be 34. And the square root will just cancel out. So now we're going to distribute this. This is another case where I'm just going to be on the safe side and type this in a calculator. If I can do it mentally pretty easily, I'll bypass the calculator. But I've got no problem at all with relying on the calculator to do arithmetic. That's beyond quick mental. That's just taking too long to calculate mentally. So let's see here. We've got 23 over 34. Times 3. Oops. Is going to be 69 over 34. And then our vertical component would be 23 over 34 times 5. So we get 115 over 34. Okay, and there's our projection vector. For number 4, we're looking at two 3-dimensional vectors. So we'll solve it kind of like how we did number 2. In fact, let's just copy and paste the work here because it will be basically the same. We're just going to change some numbers around. So the dot product for A dot B will be 2 times. Now notice in B, this is kind of what I was referring to before. We're missing the I component here. We're missing that horizontal component. So it's just like 0I. Okay, so we've got 2 times 0 plus -1 times -3 plus, looks like 1 times 2. And then the magnitude of vector A would be 2 squared plus 1 squared plus 1 squared. And the vector we're projecting onto, A, is going to be 2, -1, 1. So now we're going to simplify all this. All right, so just ignore those arrows for the moment, and let's simplify everything. So 2 times 0 is going to be 0. -1 times -3 will be +3. 1 times 2 is going to be 2. So 0 plus 3 plus 2 is going to be 5. And down here we've got 2 squared is 4, 1 squared is 1, 1 squared is 1, so that would be 6. And then squaring a square root, once again, cancel out, so we get 5/6. And so we're going to distribute the 5/6 to each one of these. So 5/6 times 2 would be 10/6, which does reduce. We don't really need a calculator for this one. This reduces to 5/3. 5/6 times -1 would be -5/6, and 5/6 times +1 would be +5/6. All right, so there's number 4. Let's take a look at number 5. We're moving right along here. All right, for number 5, let's see. We've got 2-dimensional vectors here, so I'm going to copy and paste my work from up here. We're going to find the dot product of the 2 vectors first, so that'd be -4 times -1 plus 8 times -1. And then for the magnitude of the vector that we're projecting onto, we've got -4, just 4 squared. When you square it, it doesn't really matter if it's positive or negative, plus 8 squared. And then the vector we're projecting onto is right here, -4, 8. So let's go ahead and simplify all this. -4 times -1 is going to be +4. 8 times -1 is going to be -8. So 4 minus 8 is -4. And then, let's see here, 4 squared is 16, 8 squared is 64, 16 and 64 would be 70, 80, exactly 80. So, let's see, square root, those cancel out, and now we're ready to distribute the -4/80ths to -4/8. So let's reduce this since we can. Divide both these by 2 would be -2 over 40, and then it looks like we can reduce one more time to -1 over 20. So when we distribute this, we get 4 over 20, and we get 8 times 1 would be, or -1 would be -8 over 20, and both of these can be reduced. 4 over 20 becomes 1/5, and -8 over 20 becomes -2/5. And there's your answer for number 5. Number 6, looks like we have one last projection vector that in 3 dimensions here. So let's start by finding the dot product. A lot of zeros here, so this should work pretty easily. Hopefully we don't need a calculator. 0 times 3 plus 10 times 5 plus 0 times 7 all over the square root of 0 squared plus 10 squared plus 0 squared. And then the vector we're projecting onto is 0, 10, 0. So it's just going 10 units in the vertical direction. So let's go ahead and simplify what we've got there. 0 times 3 is 0, 10 times 5 is 50, 0 times 7 is 0, so 0 plus 50 plus 0 is just 50. And then 0 squared is 0, so that goes away. 10 squared is 100, and 0 squared is 0. The square and the square root cancel each other out, and so we get 50 1/100ths, which reduces really nicely to 1/2. How about that? So now we're going to distribute the 1/2 to each of the three components. Half of 0 is just 0, half of 10 is 5, and half of 0 is 0 again. So, yeah, so there's our projection vector. Let's see if I can make this box a little smaller. Doesn't need to be that big. There we go. Okay, so that's it for the front page where we're just calculating projections. Just really important that you make note of like which vector are you projecting onto, and which, the one you're projecting onto you want to think of like as the floor, and then the one that you're actually projecting, in this case B, onto A, B is going to be what is causing the shadow, and the projection is the shadow vector itself. All right, so let's take a look at some physics problems here. Okay, so this is going to require a little information about how we calculate work, and it looks like we got 3 problems here. So let's just work these one at a time. On number 7 here, we're trying to find the work done by trying to drag this table across the floor. So we're pulling with a force of 45 pounds at this 30-degree angle measure, and we're dragging it 20 feet. So I went through in the lecture and kind of went into more detail. I kind of, looking back at it, I feel like I made it more complicated than it really needed to be. But ultimately what you need to do is just multiply or find the dot product of the displacement vector and the force vector. Okay, so the displacement vector here is going to be this 20, 0, because we're dragging it 20 feet to the right. Okay, so 20, 0. And then the force vector is going to be this vector right here. So to find the horizontal and the vertical components of this, this is something that we did in the previous lesson, where we multiply the magnitude here, which is 45, by cosine and by sine of the direction angle. So the horizontal component would be 45 times the cosine of 30, and the vertical component would be 45 times the sine of 30. So I don't want to say that in the lecture video what I said was incorrect, but this is going to be, I think, a way easier way of kind of getting to the answer here, is just find the dot product of these. So in other words, like the amount of work done is equal to the displacement vector times, let's get that dot, since we're doing a dot product, times the force vector. So the work done here is going to be the dot product of 20, 0 and 45 cosine 30 times, comma, 45 sine 30. And since we know how to find the dot product, this should be pretty easy to calculate. So here we can kind of avoid, the whole, finding the projection and all that. This is going to be a much more direct way of getting there. But let's go ahead and start calculating this out. So this will equal. First thing I want to do is simplify these expressions. Okay, so using my unit circle, I can identify that the cosine of 30 degrees is root 3 over 2, and then sine of 30 degrees is going to be 1/2. So I'm just going to kind of leave this here alone, since we're going to be putting it all in the calculator at the end anyway. So let's see here. We've got 20 times the 45 cosine 30, and that's in degrees. Throw that little degree symbol in there. Oops. There we go. Plus 0 times, and notice, with the 0 times, it doesn't really matter what I'm going to multiply by because it's just going to turn out to be 0 anyway. So, but I'll throw it in there just to let this be complete. And then, so let's go ahead and throw this in the calculator. We've got 20 times 45 times square root of 3 over 2. We could give an exact answer here since it is one of those common angles, but I'm going to just get a rounded answer here. There we go. So we've got 20 times 45 times the cosine of 30 degrees. And so we get approximately 138.826. Now, as far as the units are concerned here, this is going to be pound feet. It's kind of a weird unit here. Pound feet. I don't know. Yeah. Kind of a weird thing here, but that's what it is, okay? Or, wait, hold on, I'm sorry, not feet, pound feet. It should be foot pounds, jeez. I don't know if that makes it any better or worse, but that's just what they're called. Yeah, kind of a weird unit there, but 138 foot-pounds. So that represents the amount of work that would be done if you drag this table across the floor with a force of 45 pounds at 30 degrees. So, all right, let's look at the next one. So each one of these we're going to work very similarly. Really, it doesn't get any easier unless you're dragging at the same direction like the force vector is in the same direction as the displacement vector. So let's get rid of this calculator and read the next one. A tractor pulls a log 800 meters, and the tension in the cable connecting the tractor and the log is approximately 15,691 newtons. Just a little heads up, this is a unit of force. So that is basically giving us the force, the information about the force vector. The direction of this force is 35 degrees above the horizontal. Approximate the work done in pulling the log to the nearest joule. And we are pulling it 800 meters. So it's basically like the same setup as we've got up here. We've got this object, okay, this log, which I'm just going to draw a circle for, that's being pulled at a, 35 degree angle measure. So this right here is 35 degrees. And the force is 15,691 newtons. And then how far are we? 800 meters. Okay, so this distance right here is going to be 800 meters. So a very similar setup to the last one, except our units are different. And one quick note here, and I did mention this briefly on the notes, that if you have a Newton meter, like a foot-pound doesn't have like a fancy name for it, it's just called foot-pounds, but a Newton meter does have a fancy name. It's called a joule. Okay, so if your work is in Newton meters, you can call it a joule. If you call it Newton meter, that's not wrong, but joule is just a more conventional term for that particular unit. So let's go ahead and basically do the same steps that we did in the previous problem. My displacement vector here is going to be 800, 0, because we're dragging it 800 meters. And then our force vector is going to be 15,691 times the cosine of 35. Now, 35 degrees is not going to be one of our common angles on the unit circle, so we are going to be stuck with the calculator here no matter what. Let's go ahead and fix all this while I'm noticing it. There we go. Okay, so yeah, so we got 15,691 in this case times the sine of 35. So when I go to calculate the dot product, oh, I don't know why I typed that twice. I don't need that twice. We've got 800 times 15,691 times the cosine of 35 plus 0. So again, like this second unit is not really, it's not doing anything. We're multiplying by 0, so it's not going to affect our final answer here. But I'm still going to record how we would calculate it just in case. Really, the only time that's not going to be 0 is, let's say you are dragging this up a hill or something, or you're pulling it up off the ground. But as long as you're moving horizontally, there should be no vertical component to your vector there. It should just be 0. So anyway, we're going to type this in the calculator. We don't need to worry about all this. We're just going to type this in. So let's go ahead and do that. Pull up the calculator here. And so I've got 800 times, what is that, 15,691 times the cosine of 35. That doesn't seem right at all. Oh no. Okay, I should have been in degrees. Oh goodness. So that means I need to go back and I need to fix that previous problem. Yeah, that should be 779, my bad, y'all. So let's go ahead and fix this first. What have I done here? What have I done? All right, this should be 700, should have knew something was up there, 779.423. All right, now I've got that fixed. Yeah, as soon as I see that negative, I'm thinking, hold up, something ain't right. Okay, so now that we've got that fixed up, let's go back and calculate the number 8 here. Gosh, what a pain. All right, that is a huge number. Yeah, that's what it is. So let's go ahead and write it down. There's no commas in here, so I'm gonna do my best to let's figure out to read it. Let's throw some commas in so it's a little easier to read. And this is not going to be in foot-pounds. This is going to be in joules. So it looks like it's, throwing some commas here, 10 million, a little over 10 million joules. We'll just call it, say, rounds to 10 million. At that scale, that's huge. Okay, so there's number 8. All right, well, let's wrap this up with number 9. It says a force of 20 newtons is applied on an object of 25 degrees, causing a displacement of 10 to. Okay, so this one's going to be a little different because we are not pulling it directly to the right. Okay, so in both of these previous examples, since we're pulling it directly toward the right, you can see we multiplied by 0. There was no vertical component to our displacement. But this one does have a vertical component to the displacement, so you're not only pulling it to the right, but up a little bit. So let's go ahead and calculate this out. So let's copy all this. All right, so we've got a force of 20 newtons applied at an angle of 25 degrees, causing a displacement of 10, 2. So we have our displacement vector, 10, 2, and we've got our force of 20 newtons. And the angle is going to be 25 degrees. So let's go ahead and actually calculate the dot product here. We've got 10 times 20 cosine 25, and we've got 2 times 20 sine of 25. So let's go to the calculator. 25 is not one of our common angles, and so we are definitely going to use the calculator to compute this one. We've got 10 times 20 times the cosine of 25 degrees. Let's make sure we're in degrees here. Yeah. All right. And then plus 2 times 20 times the sine of 25 degrees. All right. So we get approximately 198.166 joules of work. And that pretty much wraps it up for this homework, okay? As always, if you guys if you have any questions or want me to go into more detail on some of these problems, let me know. And other than that, you guys have a great day, and I'll see you next time.